Okay, so now we're going to see, the first part was a bit dense, this one will be a bit lighter, and we're going to see how we can modify the support vector machine to handle some misclassifications, so not to crash or break down when we cannot separate our classes. This will be the soft margin support vector machine. And more importantly yet, we're going to see this kernel trick. So this is a way to use the support vector machine to implicitly and cheaply do that same kind of thing we saw with logistic regression, where we transform our data into higher dimensions with nonlinear transformation. And we're going also to see how regularization works in support vector machines. So let's start with the soft margin. We saw this linear support vector machine, and this works if the classes are linearly separable. So if we have something like this, we can find the support vectors, we have a solution to this maximization problem with those constraints, and we can find the discriminant. However, this does not work if the classes are not linearly separable. And the reason is that if we have, intuitively we can see this, if we have some points that are surrounded or very close to points in the other class, then we can have a large negative value here that can be made as large as we want by increasing the corresponding Lagrange multiplier. Since this negative value will change sign because of that minus there, we can increase this function to infinity by increasing the Lagrangian multiplier to infinity. And so we don't have an answer to the maximization problem. The function simply explodes to infinity and we cannot solve the problem. So this is what happens when the classes are not linearly separable. We have points that are too close together to neighbors of the other class, something like this, for example, and now we cannot find a solution. So if we try to solve the linear SVM problem, in this case, we don't have a solution because the Lagrangian multipliers just go to infinity. So how can we solve this? The reason why we cannot do this, if we look at it more formally, is that we cannot impose this constraint. This constraint becomes impossible to impose because no matter how large we set the W, there will always be points that are on the wrong side of the discriminant. So what we can do is we add a slack variable here. So we give some tolerance, we soften the margins, and we allow for some tolerance in this value. So what we're saying is that for each point n, this value, so the inner product with the vector that defines the discriminant and the class, must be at least 1 minus this tolerance value, this slack value, that we impose each slack variable for each of the points. So each point can have its own slack and can be either inside the margin, if this is larger than 0, or even on the wrong side of the discriminant if this value is larger than 1. So if this value is larger than 1, we can even have a negative value there in that sign distance. This means that the point is on the wrong side of the discriminant. So we allow this flag, but we impose this constraint. The total sum of all the slack variables we add as a penalty as part of the function we're trying to minimize. So we are minimizing the size of the vector that defines the discriminant plus the total sum of the slack variables multiplied by some constant. So this is a way of softening the margin, and we can do this. We change the expression here. We can do exactly the same thing. I'm not going to go through all the steps again, but basically we have this constraint optimization problem. We compute the Lagrangian for this, and we have the dual problem and so on, and we get this Lagrangian, which includes this slack, this C variable for the slack. But when we go to the dual, we solve for the derivative, we have exactly the same expression. So even though we added these variables for the slack, we have the same expression, but we have these different constraints. So now we have a constraint because of this expression here, and this ends up adding another constraint. We already had this constraint that all the Lagrangian multipliers must be 0 or more. But now when we add these slack variables multiplied by this C value, this amounts to adding an additional constraint that the Lagrangian multipliers cannot be larger than C. So this is what we end up with after doing again all the derivations there. So what does this tell us intuitively? We had this problem when one point was on the wrong part of the discriminant, or inside the margin, or on the wrong part for each class. We could increase the Lagrangian multiplier arbitrarily because this part would be positive, and we would explode and go to infinity, and so we don't have a solution. If we impose this constraint, what we're actually saying is that the Lagrangian multiplier cannot go higher. That is, the penalty that we are imposing for points that are inside the margin or incorrectly classified cannot be larger than C. So this way we guarantee that we always find a solution. We always find that maximum. We can do the same thing. So this is basically what I showed before, but the bounds for the alphas have this upper value of C instead of none, instead of going to infinity. And now we can find a solution for this problem, which was not linearly separable. Note that we have here a set of support vectors. So these are all the examples for which the Lagrangian multiplier is not 0. These are relevant examples. In black, we have those for which the Lagrangian multiplier is between 0 and C. So it's within, those that are at the margin. And then in red, we have those other examples for which the Lagrangian multiplier was maximized at C. So this means these are incorrectly classified or inside the margin, and the Lagrangian multiplier reached the maximum that we imposed. So in this case, C was equal to 0, and this is an example of a support vector machine with soft margins. We allow some points to go inside the margin. If we look at the support vectors to compute the values for this discriminant, so the values for the W vector, we'll use all the support vectors to compute W, but then we have to take care of this additional parameter W0, that we can only use those support vectors that are at the margin. So those that for which the Lagrangian multiplier is between 0 and C. The reason for that is that we are using the expression that tells us the sign distance for those vectors must be 1, and if the vector is inside of the margin, this is not true. So we would get an incorrect value. So basically, we use all these points to compute the vector that determines the direction of this line, but we only use the points in black to determine the position of the line, because we cannot assume that the others have a sign distance of 1 to the discriminant. So this is just one modification, but basically what we are doing is to soften the margins, we are imposing a limit on the Lagrangian multiplier, and here we can see the values for all the Lagrangian multipliers in this example. You see that most of them are 0. So basically, this 3.9 times 10 raised to the minus 15, this is 0, it's close to the precision for the floating point. So these are all effectively 0 minus some rounding error. But there are a few here. You see this one, this is 10, 1 E1, so 1 times 10 raised to 1. This is 10, this is 10 here. So these are the ones for which the Lagrangian multiplier was maximized, and these correspond to these in red, which are inside the margin, or even on the wrong side of the classifier. And then we have these support vectors, for example, here, 2.5, or there are others here, 6.6, and so forth. These are the support vectors that lie at the margin. So these have a Lagrangian multiplier that is greater than 0, but not as high as C. So this is the idea for the soft margins. We impose a limit on the Lagrangian multiplier. It allows us to have some points inside of the margin, or even misclassified, but those will maximize their Lagrangian multiplier. They will reach the limit and will not go beyond that because we are imposing that as a constraint. The support vectors that are at the margin will be those for which the Lagrangian multiplier is below the limit, was not maximized in this way. So we have these here. This is misclassified, you see. So this is actually the select variable was greater than 1 for this case. These are inside the margin, and then there are these three in black, which are those for which the Lagrangian multiplier is greater than 0 and below c. All these outside the Lagrangian multiplier is 0. It's not exactly 0 because of rounding errors, but it's 0. They are not support factors. Yeah. We can choose the value of c depending on the data by cross-validation, for example. So if we want to use soft margins and we don't know what c we're going to use, we can do cross-validation. So basically, this is a regularization problem where we change the c. It's the same as we saw in other examples. Okay? And this, by the way, is the reason why you have this c also in logistic regression and so on in the scikit-learn. So to make everything uniform, you have always this notion of the c, even though in logistic regression it's not so intuitive why it should be the c. So now let's go a bit beyond this, because with soft margins we can solve problems like this, where it's only slightly nonlinear and we ignore those incorrectly classified. But if we have something like this, then using soft margins will not result in a very good classification. So basically, we are trying to do a linear classification here, a linear discriminant, but this is very nonlinear and it will give us a lot of error. So how can we solve this problem? We have a linear classifier. We have two classes that are not linearly separable, and we saw how this was done. With logistic regression, we did that nonlinear expansion and kept the linear classifier in higher dimensions. With the neural networks, we transformed in the first layer the data so that the second layer could classify. So this is the basic idea. We're going to transform this data. In this case, we're going to project it nonlinearly in higher dimensions, but we're going to take advantage of this kernel trick. So we're going to use kernel functions to do this cheaply without having to do it ourselves, computing all the results. So the kernel trick depends on this kernel function. We already saw this name in kernel density estimation, and unfortunately it's the same name for two things that are very different. But I'm not to blame for that. It was already like that when I met it. In this context, a kernel function is a function of two vectors that is equal to the inner product of the image of each of those vectors transformed by some other function. So basically, we have this function here that transforms each vector, and we can compute the inner product of the transformed vectors using this k function, which is the kernel function. It's a function of the two original vectors. I'm going to give a specific example to make it easy to understand why this is useful. Suppose that we have this transformation that takes one vector of two coordinates, x1 and x2, and transforms it into this vector that has 1 square root of 2 times x1, square root of 2 times x2, then square root of 2 times x1 times x2, x1 squared, x2 squared. So we have this vector of 7 dimensions, where we first had 2. We transformed it into 7 dimensions, where we have square terms and product terms, so this is a nonlinear transformation. The inner product of two vectors transformed by this function, so from 2 to 7 dimensions, is the same thing as the inner product of the two original vectors in 2 dimensions, plus 1 and then squared. So this is a kernel function for this transformation here. And this is much easier to compute because these vectors are in 2 dimensions and these are in 7 dimensions here. And we can go higher to much more dimensions. In general, a kernel function for this kind of polynomial expansion, which is similar to the ones you did with logistic regression, if we want to raise it to n, so this will increase dimensions a lot. It's not just 2 to 4, it's to 7, and then goes on from there. But we can do this, a polynomial expansion of degree n is simply the inner product of the two vectors plus a constant raised to n. So this means that we can do polynomial expansion very cheaply without explicitly transforming the vectors if we only consider the inner product. Now, for logistic regression, this is not useful because we don't use the inner product. We need the actual vectors to train logistic regression. But with support vector machines, we only look at the inner product of the vectors. So if we replace that inner product with a kernel function, we are actually training the support vector machine as a linear classifier in that expanded dimension after the transformation, but we are doing that without having to compute all of these things. We just compute the kernel. Because since the support vector machine only looks at the inner product of the vectors, we can skip that step of actually transforming the vectors and just pretend they were transformed by using the kernel function. So this is the perhaps most interesting and powerful feature of support vector machine. It allows us to do what we saw before with neural networks and logistic regression of transforming the data non-linearly into another representation, but to do so cheaply without actually having to compute everything. As long as we find kernel functions that are easy to compute, we can do these transformations implicitly without the computational cost. So this is the kernel trick for support vector machines. We find a kernel function that computes the inner product of the transformed vectors for some nonlinear transformation to higher dimensions. And then we substitute those inner products with the value of the kernel function, which generally is simple to compute. And then we are training the support vector machine as if we were doing it in the higher dimensional space. Now, to classify new points, we cannot do as before. We cannot compute the W or W0 and then classify the points, because now, if we use the kernel trick, the discriminant will not be in the original space we are using. So, for example, if we use this kernel here, the discriminant will be in 7 dimensions, in this space of 7 dimensions, because it's being computed as if the vectors were transformed by that transformation. So if we do that for hundreds of dimensions, or millions of dimensions, or even infinite dimensions in some case, we cannot compute explicitly the W. But we can keep the support vectors, and then we can compute the class of each point, because we know that this signed distance, so of the hypothetical, the theoretical discriminant multiplied by the vector after the transformation would be negative on one side and positive on the other, and this can be computed by simply multiplying the Lagrangian multiplier of each support vector, each class, and the kernel function applied to that support vector and the point we're trying to classify. So if we do that for all the support vectors, we get something that's either negative or positive and gives us the distance to the hyperplane there. So we can ignore the W and W0, keep the support vectors. We need to remember which of them are the support vector and what are the coordinates, and then use this expression to classify the points that we want to classify. So let's see an example here. Let's suppose that we have this polynomial expansion to degree d. We just use this expression here. We compute the inner product and raise it to the power of d after adding 1. And this is what we do to compute the new H matrix. So instead of computing the H matrix as simply the product of the classes and the inner product of the vectors, we add this transformation here to do it implicitly. So we replace the inner product with the kernel function. And now, to evaluate, to classify a point, we simply take the support vector and we compute this value here. If it's positive, it's on the positive side of the hyperplane. If it's negative, it's on the negative side. We never compute the actual hyperplane, because if we do this with a large D, we can easily go into hundreds of dimensions, and we don't really want the hyperplane in hundreds of dimensions, because we never actually transform our data into that space. We simply compute the inner product as if the points were transformed there. So this is the kernel trick. We are doing the depth transformation cheaply by using kernel functions to give us the same result as if we had transformed the data. We're not going to implement this in this way, because then you can get into trouble with the minimization and so on. We're going to use the support vector classifier that comes with scikit-learn, because it's optimized for solving these kinds of problems, and you won't have so many problems with the optimization part. So basically what we have here is we have as one parameter the C value, that is for the soft margin. The lower the C value, the softer the margins will be, because that is the highest value the Lagrangian multipliers can have. Then we can choose the kernel. In this case, this is a polynomial kernel. Depending on the kernel, there are other parameters for specific for the kernel. So in the case of the polynomial kernel, we have the degree here, and then we can use the fit function to fit all our data, and then we can plot. Basically, these plots are similar to the code I show you on the tutorial classes, where we evaluate the values for a mesh of points here, and then we can color or draw in the frontiers. However, these kinds of plots are not useful in general. I just use them a lot because I always show examples in 2 dimensions so we can see these. In practice, you will seldom be able to see these kinds of plots, but at least you know what's going on. So this is an example of a polynomial expansion with degree 2 and using a C of 1. This C value of 1 means that the Lagrangian multipliers can only go up to 1, so the margins are very soft. In fact, we can allow a lot of points to go into the margins this way. If we use a degree of 3, we have more curves. So actually, this is the same thing as we saw in the logistic regression. We are expanding to higher dimensions. Only in this case, we don't actually pay the cost of that expansion, because we are using the kernel, and we just adjust the degree there for the kernel. If we increase the C value, we narrow the margin. This happens because a higher C value means that the Lagrangian multipliers can be higher, the penalty for falling inside the margin can be higher, and so we will shrink the margins here. The function will change more steeply. This is the same that happens when you reduce regularization with logistic regression. You allow the W values to be higher, allow the function to change more steeply, and so the step between one class and the other is shrink there. So basically, as you increase C, you reduce the strength of regularization, because you are penalizing more points that enter the margins, and you are forcing the margins to be narrower. And this is why, when you use in scikit-learn logistic regression, you have that penalty for the size of the vector to be 1 over C. So the idea is the same. As you increase C, you reduce regularization. Okay? So this is standard over the library, and it's mostly based on the support vector machine part. Now, if we use very high C, we have very narrow margins, and we eventually don't have points entering the margin. Because now, if you use a value that is higher than all what the Lagrangian multipliers will be with this data set, then in fact we don't allow any to be inside the margin. We can use other kernels. The Gaussian kernel is a function, also called radial basis function, that has the shape of a Gaussian in the dimension of the original vectors. And actually, this is a kernel function for a specific transformation into infinite dimensions. So you can curve as much as you want when you use a Gaussian kernel. Intuitively, the idea is that you're doing something that is similar to when you use a Gaussian kernel with kernel density estimation, or when you use nearest neighbors, because as you decrease the radius of the kernel, you're going to look locally at the points nearest. So if you decrease it too much, you can get something that cuts away all the points, looking only at the neighborhood. So in this case, we're going to use the RBF, radial basis function kernel. We set this gamma value here. So in the Gaussian function, you have this e raised to the size of the vector there, divided by the standard deviation, and that 1 over 2 sigma squared is what is gamma in this implementation. So you can control that value here. And basically the effect would be, if you use a small gamma, this changes smoothly, so we are looking at longer distances, and we have something like this that is very, very coarse. If we increase gamma, we start looking more at closer points and less at the most distant points, so we can increase the way the frontier cuts. We can also change the C value, so for example, if we use a large gamma with a large C, we have a very intricate margins here, cutting away the shape there. If we use a smaller gamma, we have a more smoother frontier, and also we can use C for setting the size of the margin. So basically, we have these C values that affect regularization of the support vector machine, so allows us to increase the size of the margins. But we also have these parameters for the kernels that we use. Depending on what kernel we use, they have different meanings. But the idea is that we are doing expansions into n dimensions, and we are changing the shape of those expansions, so to speak. So basically, this is the idea of support vector machines. We can use soft margins by setting a limit on the magnitude of the Lagrangian multiplier. Actually, the idea of the soft margins is to add those slack variables, but when we derive everything, it ends up just being an upper bound on the Lagrangian multiplier. So this is basically, we are allowing points to enter the margins because we are limiting how much that can penalize the function that we're maximizing. We also can do nonlinear classification with support vector machines. So even though support vector machine is always a linear classifier in the dimensions where it's actually working, we can use the kernel trick to make our support vector machine work in an arbitrary number of dimensions without having to pay the cost of actually computing the vectors there, because we just replace the inner product with the kernel function, and we compute as if we were in that higher dimensional state. This means that with support vector machines, you can really go wild on this higher dimensional expansion. You can have lots of problems with overfitting, but if you use cross-validation and try to fine-tune the parameters, you have a lot more flexibility than what we had if we do it manually with logistic regression, for example. It also means that in practice, you're not going to do what we started by doing with logistic regression, doing the expansion manually. That doesn't make much sense, because if you want to do that, it's better to use the support vector machine. But the idea behind doing this manually was to make it easier to understand why this is powerful in support vector machine. Because if it's just a black box, it's very hard to understand what's happening. Okay? So this is what we have in the kernel tricks. You have in the documentation for support vector machine in the scikit-learn, you have other examples of kernels that you can use. And then we saw how we can do regularization in support vector machines with soft margins. So basically, the model is the same, so to speak, but we change the maximum magnitude of the Lagrangian multiplier in order to change the final result. So we have these sections in Bishop, Marsland, and Alpiden that you can look. They cover mostly the same thing, but sometimes it's useful for you to see the same thing explained in different ways. It may help understand.